Welcome to Homework Lib.
So this problem asks us to find a few things regarding an ionic system involving potassium, which has a positive charge, and bromine, which has a negative charge. In part A, we're asked to calculate the electric potential energy for these two ions when they're separated by some distance r of 0.29 nanometers. So if we're assuming that these are point charges, like the question asks us to do, then that should call to mind the Coulomb potential. So it's written in a few different ways. You've probably seen it with Coulomb's constant here, which can also be written as 1 over 4 pi epsilon naught, the permittivity of free space, multiplied by charge 1, charge 2, divided by r, the distance between the two charges. In this case, r charge 1 is whatever the charge of this potassium ion is going to be, which is just the elementary charge, i.e., the charge of one electron, but positive. And conversely, it's almost the same for charge 2, except now it's going to be negative because bromine has a negative charge. So that's a positive elementary electric charge and a negative elementary electric charge. And then, of course, R is just the interionic distance given here in the problem. So if we fill in some things here, we have our constant multiplied by charge 1, which is a positive E, charge 2, which is a negative E, and divided by R, which we determined earlier is what's given as 0.29 nanometers. So if you plug in for all of this and keep track of your units and your unit conversions, you should end up with a potential of negative 4.97 EV. So this negative shows you that you have an attractive potential, which, if you look to the text, is what you expect for such a thing, because if this is V and this is R, you expect that this location is where you have the minimum for things that are of opposite charges. And that's what we find here. So this VC is the energy at this location. So that's part A, parsed and understood. Then we can move on to part B, which asks us to find the binding energy of the calcium bromide molecule. And so to find the binding energy, what we want to do is take our potential energy, which we've been calling VC, and then subtract the energy cost of bringing these two ions together. So that means we need to subtract the ionization energy of the potassium, so what it takes to pull an electron away from potassium, and the electron affinity of bromine, which is how badly the bromine wants to take in a electron. And so the numbers are given in the text here. This is 4.3 EV subtract 3.5 EV which is just 0.8 eV. And this number, you can interpret this as the energy cost of moving an electron away from the potassium and to the bromine. So then plugging in for this and using our value that we found earlier for VC, which I'll write again here. I'm going to write this as positive because there's a subtraction involved. 4.97 eV. Thus, the binding energy is, if you look at it as a positive value, 4.17 electron volts. So we'll put a box around this. And that fulfills the first part of the part B's question. However, as it correctly points out, this is just an estimate. So the things that we have neglected beyond just considering that they were just point charges was that there's no additional kinetic energy in this system. So that means the ions are not shaking about at all. That's a crude drawing, but it works, I guess. So the situation where there's no kinetic energy is, of course, a situation where you have no heat. That'd be at absolute zero, which nothing lives at, obviously. And so this value here can be assumed as a upper limit of what the binding energy can be. If you start to shake the ions a little bit, the binding energy is going to be a little dampened. It's going to be more likely to come apart. So you can assume that in real life, the actual binding energy is going to be actually a little bit lower than our estimate. And sure enough, if you go and look to some calculation, you'll find that the actual binding energy is around 4.06 eV. I assume this is at room temperature. So there's certainly some things that can change these answers depending on the conditions that you're considering in your problem.